Thank you.
You're welcome. Okay, so you understand counter, easy one. Counting the number. You want to count 0, 1, 2, 3, 4, 5, 6 up to any number. That's what they call counting up. If you want counting from 15, 14, 13 going down, that's what they call counting down. And the first thing, we get two different types of the counter. One we call a synchronous counter or the ripple counter. And another one will be synchronous counter. Ripple counter will be more easier to design. Basically, the counter you count by decimal. 0, 1, 2, 3, 4, 5, 6 to whatever number. However, the computer understands only binary number. Okay? And also, computer can understand decimal number. The reason is, when you type in the decimal number in your keyboard, they get a device to converting that number to the binary number. Okay? So if you're looking on this circuitry here, they're using 2 flip-flop, JK flip-flop. If they're using 2 flip-flops, so what the counter can be counting from what number to what number? I can give you example.
0 to 3. So 4 numbers, 0 to 3.
Yeah. Now you get a 1 D flip-flop. If this is a counter, what number they can count? From what?
Two, 0, and 1.
Exactly. That means the counter output still, either they can be 0 or they can be 1. That means they only count 0 to 1. If you get a 2 flip-flop, then they count the first one, you can see they get a 0, 0. That means 0. The next will be 0, 1, right? Number 2. And the next one they counting that number 1, 0, 1. 0, 0, 0, 1, number 1. Okay, so that will be 0. Next will be number 1. And the next one will be 0, 1, number 2. And the last one, number 3. So if you get 2 flip-flop, they can counting from 0 to number 3 in a decimal. And now you try to understand, okay? basic counter, then the rest will be very easy. First thing, this will be 0, 0. That will be 0, 1, 1, 0, 1, 1. Okay. So normally they draw this one. What that means? When you see you get a 0, 0, that's what they call a state. 0, 0. So if you see the arrow going this way, what happened? What does that mean to you? Look like exactly when you get a 0 here, 0 here. If they draw that arrow here, only they counting you. They stay in this state, 0, 0. Stay forever. However, when you get a clock, they go to number 1. Okay? That means when you apply the clock here, then they will be go to number 1. And if you get a 0, 1, you don't have a clock, they still stay in this state. And if you get a clock, they go to the next one. Exactly the same thing. Okay? So, the counting number, if you're using decimal, they will be going from 0, 1, 2, 3. However, how many states? They will be 4. 0, 0, that's step 0. 0, 1, the next one, 1, 0, 1, 1, okay? The number of states will be 4. However, if you're talking about decimal, they only 0, 1, 2, 3. And that also telling you, if you want to counting, like you get a 2 flip-flop, you want to know what the decimal number they can count up to, then you can using 2 power of n. If you get only 2 flip-flop, 2 power of 2, you get a 4 state. And a decimal will be less than 1. Two power of n minus 1. That's why you get 3. If you start counting by decimal. And this is the timing. Okay? Timing to show you. This is a clock applied. J and K flip-flop when they tie JK to high. That means the flip-flop only toggle. Okay? That means it's 0. You apply the clock. Toggle, they go 1. If they want, you get a clock, they go to 0. And also, if you're looking at a timing, clock will be a negative going. This is negative going. So the first one, you get a 0, 0. When you apply the clock, they go to the next will be 0, 1. Okay, when you get another clock, they will be go 1, 0, and so on. So you get 2 ways to testing this counter. You can build a circuitry. You can apply 10 kilohertz size. TTL logic from generator. So if you get a 10 kilohertz, what the frequency for QA? If you're looking at a timing,
5,
telling me if you apply 10 kilohertz clock, what the frequency at the output of the first flip-flop A?
5,
Exactly. 5 kilohertz in here. What frequency at another one?
2.5,
2.5. So if you're looking on the timing, you can see easy. Okay. For the output from here to here, one period, that will be double. Okay, the period of the clock. So that's why they get only a half. And next one, you can see the same thing. From here to here, that's the period QB. And basically QA will be the clock of QC, of the QB. So that's why they double QA. That's why they only 2.5 kilohertz. And that also they can say this is the divide frequency. The first one divide by 2. And the second one divide by 4. That divide by 2. And that will be divided by 4. That means you take a 10K, you divide by 4. And you can get 2.5 kilohertz. You understand in the computer, they get the only master clock. How many gigabyte, gigahertz, sorry. Okay, however, inside the motherboard, they're not only using that master. They can using a different frequency depending on the circuitry. So in order to get a different frequency, they're using divider. Okay, divide by 2, by 4, by 16, by whatever number. Okay, so how do we recognize ripple counter? Okay, ripple counter, they're telling you
Mr. Pham, question?
just a minute. Ripple, that means the output of the first flip-flop connect to the clock of the second one. And now if you get one more flip-flop, then the output of the second flip-flop will be connected to the clock of the next one. That keep going. That's what they call ripple. Okay? And a synchronous counter is one in which the flip-flop within the counter do not change state at exactly the same time because they do not have a common clock position. That means this is the clock going only the first flip-flop. Okay? And the second flip-flop will be get the clock from output of the first one. If you tie clock everything together, that will be synchronous counter. Okay, go ahead, question.
Can the frequency division be infinite? Where it actually zeroes out or becomes something different?
What do you mean frequency?
Well, you're saying that in the division from 10K down to 2.5K,
Okay,
it looks as if there's a possibility that if n is the value, is n considered to be infinite in how the frequency divides itself? Can it divide itself to where it's literally zero, where it cancels out the frequency, possibly?
now you can see the timing and you can calculate the frequency. You see that at one period, right?
Yeah.
What the frequency, what the period for QA? QA from here to here. They double T, right? The thing I did is from here to here 1T, from here to here 1T. Okay, so you get another T right here. So that the period QA will be 2T. When you increment the period, the frequency going down. So if you get 10K, then the output have to be 5K. And now if you're looking on the next one, okay, you can see from here to here, that's one period of QA. And QA that go into the clock here. So now the output of QB, you can see, this is 1T. They double of the period of QA. So that means they will be 4 times, okay, more than for the period. That divider. By looking into the timing, then you're able to see what the frequency is supposed to be at the output. And now, the other way, you can testing the circuitry using the binary. So the first thing is you can see the output here will be 0, 0. Okay. And now if you apply the clock and you can get this one, that will be 0. You can read it, binary verify that. But there must be a logic. Okay, now you can see this is the same thing. Okay, a synchronous counter, but they're using 3 flip-flop. And what I'm already telling you, clock go to the first one, QA go to the clock of second one, QB go to the clock of the next one, and keep going. And for this counter, I know they will be counting how many states.
It's
How
8.
many states for this counter?
It's 8.
8, right? Okay, they're counting from 0 to what number?
0 to 7.
7.
Yeah, perfect. 0 to 7. The thing is 8 states, and the decimal will be less than 1. That means you take 8 minus 1, you get 7. So now if you understand the way organized, they can get a 4 or 5 or more flip-flop. You still counting. You know how many states and what the number the counter will be counting from 0 to 7, 0 to 15, 0 to 31, and so on. Only thing I want to make sure, when you're looking into the circuitry, you know this is a ripple counter. That is the first thing. Second thing, how many states for that counter? That will be 8. And what the number the counter can count up to. Okay, now you can see this is a synchronous binary counter. Same thing. They counting to flip-flop 0 to 3. Okay. Only the difference. You can see the clock. Clock here. They go to the first. They go to the second. They go to keep going. How many more flip-flop? That is quite different. That's what they call a synchronous binary counter. So which one will be better? A synchronous counter or ripple counter or synchronous counter? Which one you think it is better and why?
Synchronous is faster.
Exactly. Synchronous counter run faster. Why? The reason is the clock going the same at the clock of 8 flip-flop, so output will be changing right away. However, ripple, the first have to be changed in order for second to be changed. Take it longer. But easy to design a ripple counter than synchronous counter. Okay, the next, either ripple counter or synchronous counter. They can be binary counter. Or BCD. Okay, what stands for BCD? You know what that stands for BCD? binary code decimal. Okay, now if we get 4 bit, okay, binary counter. Okay, they counting from what to what?
Zero
0 to what?
16.
15.
To 15.
0 to 15.
Okay, however, 16. Okay, you get it now? Okay, we're talking about 4-bit BCD counter. Okay, counting from
0 to 9.
perfect. 0 to 9. You understand BCD mean binary code decimal. They working, using the binary, but exactly the same decimal. And in the decimal, you don't have any number greater than 9. So 4-bit BCD counter, they counting 0 to 9, then to 0. However, binary, they can go for 0 to 15 and to 0. That's only thing. And make sure, okay, you understand the difference between binary counter and the BCD counter. And for this counter here, if you want to do it, to see how they count it, you can run PSPI simulation. They will be telling you what output's supposed to be. Okay. The thing is, normally, without adding any gate for design, then you get 1, 2, 3, 4. They will be count 0 to 50. Okay. However, if they adding the gate, logic gate here, they will be make a difference. Okay, and the question about binary or BCD counter. Okay, that's still synchronous counter. This is another one. Okay, synchronous counter, up and down. If you're looking into this schematic, so the maximum the counter can count from what number to what number?
0 to 7 to 0.
Yep, exactly. 0 to 7. The reason is you get only 3 flip-flops. So basically, the state will be 8. When they add in the gate, that means they try to design, okay, different type. Now, if you're looking on up and down here, so up and down here, you can apply either 1 or 0, and you apply the clock, and they will be counted. So for counting up, what logic here?
One.
1, correct. You can see that now they get a bar over. That means active load. If you set deadline to 0, they will be counting down. Okay, now that basically counter have nothing to talk much. Only thing I want you to understand, you get a binary counter, BCD counter, ripple counter, and synchronous counter. The key thing is when you get the IC counter, what you need to know is understand how many functions for that counter and how to test it. So this is just basically IC74193. And also I also try to make sure you understand 193, 191. That will be binary counter. However, if you get an even 190, 192, so that will be BCD counter. For any different counter like 161, 163 binary, 160 and 162 BCD counter. Okay, and when you know they will be binary or BCD counter, then you know what the number they can count up to. So now in here, I try to summarize, okay, to make sure when you need data, just go to the Google, type in 74 LS193, and they're giving you what information you need to know. If you're looking on this IC here, how many pins? How many pins?
16.
16. Correct?
Yes.
What pin is power?
16.
What pin is the round?
8.
8 one right here. 8 round. VCC. The thing is I see without connect power and round, they're not working. Okay? And now they're telling you, count 74, 193. Counting up 0, 15 to 0. Counting down 15 to 0 to 15. You can load any data to the output of the counter, or you can clear the output of the counter to be 0. Why sometimes they need the function load? They're telling you, you can loading input data to the output of the counter. They try to get away from, you have to start all the time from 0 to 50. No, you can loading any data, for example, I can loading number 5 to the output. And now I can counting up, they start from 5, 6, 7. They don't have to be start from 0. That's the reason why we need loading. Okay. And now if you're looking here in the schema, in the pin layout, clear what pin number? Right here, right? 14. Okay. See what happened. If clear at the logic 1, then the output QA, QB, QC, QD, QA, QB, QC, QD must be 0. Normally, that will be a higher priority. They're telling you, if you set pin 14 here at the logic 1, then output will be 0, 0, 0, 0. So what happened to the other input? Like you can see, you can get load. Load means this pin right here. And the data input A, B, C, D. So what happened to that input output for the load or counting? The thing is, you must be understand. When you apply 1 into pin 14, you made that the output QA, QB, QC, QD, they must be 0. If they're not 0, what you need? Make sure pin 14 have to be 1. And if the output is not 0, then the IC, you don't need to check anything else. Except the power and the ground. When you do in your lab, you have to do. At work, normally, you don't. The thing is, the wire in the circuitry, you never see. They cannot be broken. So that's only telling you, when you want to test for the clear apply logic 1, the rest of the other input output will be don't care. Okay, that is clear. So try to understand on this one, you can get into the lab 193. Now, load. You see the second one. Load will be active load. This is the load right here. I know active load, the thing I see the bubble right here. That means 0 loaded. 1 is not loaded. So see what they say. This is the second priority. After the clear, the next will be control, the circuitry will be load. Okay, so in order for loading, first thing, you say load is 0. Okay. However, clear cannot be 1. If the clear be 1, you cannot load it. So clear have to be 0. So now if you get A, B, C, D, this data A, okay? Data A, where B? What pin on B? You get C here, D here, A here. Okay, right here B. So if you get a 1 here, okay, 1 here, 1 here, and 1 here, then the output have to be on 1. That means you load it. 1, 1, 1, 1. You can load in any number you want. So when the loading is not working, what you need to check, you have to make sure clear must be 0. Okay? And load must be 0. And the data input A, B, C, D. That's what you want. Then you can take the output. But you not do anything with the count up or count down. The thing is loading equals 0, you cannot count anyway. So they will be don't care. Okay? And now if you want to count up, they already telling you. Clear must be 0. Load must be 1. And the countdown pin number 4. Pin number 4 right here. Must be 1. Okay? And the clock will be applied to up. That means you apply clock into here. This must be 1 for count up. One clock they count one number. Okay? They can go 0 to 15 and to 0 forever. And the countdown, the only difference is for the countdown, then countdown now will be clock. Clock will be applied here. However, up must be 1. Otherwise, they're not working. They're telling you everything to 74.193. How do we testing for clear, testing for loading, testing for count up, or testing for count down? You get any question?
As long as 4 is 1, 5 has to be 0, and vice versa. 5 has to be 1 and 4 is 0.
What you're talking about? Which one?
Well, I'm just clarifying, just if 4 is 1, 5 has to be 0, correct? And if 5 is 1, 4 has to be 0. Based,
Okay, you're talking about up down.
right, yeah, based on your counting up and counting down. So
Okay. If you are counting down, then the clock will be applied to pin 4. However, pin 5 must be 1. That will be helping you troubleshooting when you apply the clock and the counter not counting. If you're asking me, for example, when you are working on your left, they're not counting. First thing I will be asking you, okay, take pin 14 clear. What logic? they have to be 0.
So in the transition from high to low, is the transition sensitive to when that clock is going to change from 1 to 0? Say like in a bar, current tolerance, where the transition from high to low, it could, the high to low, the transition from 0 to 1 can actually change at like halfway of the transition versus at the top
Yeah.
peak, right?
50%.
Right.
Yeah, the clock will be either 0 to 1 or 1 to 0. They're using the X trigger. Okay, now you still get the 2 more output. That's what we're talking about. Borrow, carry. I try to see. Okay, now timing here. Try to learn how to reading the timing. Everything will be coming out from timing. First thing, clear test right here. Clear go to 1. They will be clear. Okay, if you look in QA, QB, QC, QD, see that? Clear, the output will be 0. And now you want to see the load. Load 0, they loading. And you going down here, keep going down. Okay, before you want to see the output, you need to see the input A, B, C, D. Okay, A1, B0, C1. What number? One 0 1. What number?
13. It's 13.
13. Okay, so now you can see when the load is 0, you want to see output going this, going down. Okay, and now you can see, okay, the output QA will be 1, 0, 1, 1. That number 13. You can loading any number you want. However, if you're looking into the load and the clear must be 0. See that? If clear equal to 1, you cannot load it. Okay, if you get any question, just stop me, okay? These are very, very important for a technician. When you get the information, you're able how to read it. Especially for digital, they're using the timing. Okay, now, next we're talking about counting up. You can see this is counting up right here. That means they get a clock. However, now they must be at a logic 1. You going up, you see clear must be 0 and load must be 1 for count up. So basically, one clock, they will be count 1 number. Okay. They can count in the timing. They're not going from 0 to 15 to 0. Okay. They're just telling you. They counting. Like you can see when you're loading 13, when you're counting, they go to 14. Apply the clock 14. Apply the clock go 15. Apply clock, they go back to 0. And 1, 2, 3 again. Now, two things you need to pay attention. CO out. Active low. You see the bar. Over. Carry out. Normally they want. Okay. When they low. When the CO going low. If you're looking into the timing, telling me when that signal CO go low.
You counting from 15 to 0.
Now you can see up here. You see going up. Okay. You can get QA equal 1. QB equal 1. QC equal 1. And 1. They're telling you when on the output reach number 15, 1, 1, 1, 1, then they go low. That's what we're talking about, hand shaking. Okay, that's a series. Now, why we need that? You can see in your watch, you get an hour, you get a minute, you get a second. So the second counting 0 to 60. Then minute must be counting 1. A minute counting from 0 to 60. Hour will be counting 1. So how come the minute know they already get 60? So basically, they will be designed, okay? If the output of the time of the second go up to 60, then the CO go low. So the minute circuitry, they're looking into low here, and they count 1. And the same for the hour. Okay, that's what they need to carry out. Okay, so that is counting up. Remember, for 4-bit, CO go low when QA, QB, QC, QD equal to logical 1.
You say that was called handshaking or syncing?
Sharing, basically.
Sharing, all right.
The thing is that using to monitor, to let the other device know they already complete one counting cycle. They go 0 to 50. Then they go back to 0. So by looking at the CO out, I know the counter already done for one cycle, 0 to 50. Okay, any question on counting up? Now we're talking about counting down. You see, counting down. If you look up here, clear must be 0. Load must be 1. And the clock now will be go into down. But up must be 1. That's a requirement. And they telling you they can counting down. Okay, 1 to 0 and to 15, 14, 13. That's going down. Only I want to make sure you understand for borrow output BO. BO normally high when they go low.
From 0 to 15.
Yes, when A through D is 0.
QA to be 0. 0. 0. 0. They're telling you when they count down to 0 and that borrow go low. So I'm looking on the borrow output. When they go 0, I know the counter reach 0. That's just using to connect to next device. When they monitor the BO, if they see 0, they know the counter reach 0. Okay, any question? Okay, the next one, 192. We already telling you BCD counter. That's what they said. Format BCD. And they telling you count up 0 to 9 to 0. Count down 9 to 0 to 9. Load any data to the output of the counter. Clear the output to be 0. Okay. When you're looking into the function table here, if you want to test for reset, clear, MR mean master reset, logic 1. Okay. And the output will be 0. So what happened to PL, CPU, CPD? They will be don't care. The thing is clear or reset higher priority. In this case, if they high, output must be 0. So we don't care about load. We don't care about up or down. So sometimes you say, I given you the quiz and you have to be enter I for don't care. I that only telling you don't care. That means you don't have to take PL or CPU or CPD while you testing for clear or master reset. But however, when you write a program, you cannot using I. They can be either 1 or 0. Okay. However, I already telling you, we prefer a 0. That means you have to enter 0, I 0. For example, cannot 0, I don't care, no. Software in the C++, they don't understand that. Okay, now, like you want that for loading. Then reset must be low. And also you don't care CPU, CPD. Okay. So the next one, dirty low, dirty high, dirt high, dirt high. The output will be no change. That means if it was number 5, then they still number 5. If they got number A, they still number A. And sometimes you're reading on the different data book, they put Q0, Q A0, Q B0, QC0, QD0. Same thing. That is no change at the output. And if you're looking on counting up, that must be low. That must be high. Clock apply to up and down must be what? They count up. They're exactly the same. 74, 193. Only differently, one counting 0 to 15 and another counting 0 to 9. Okay? This is the timing. Try to see, can you understand? Okay? They are both the same like the other one. 191. You understand 191 is binary, up-down counter. On this, I see they don't have a clear. They don't have a reset, but they get a load. Let's see, load what number? Here. Active low. 0, you want load. 1, not loading. So you can load any number you want. Okay. And now how to make it count up? In order to count up, clock apply to what pin?
14.
Counting up, load equal 1. Okay, enable G, that's okay, equal 0. Now up pin number 5. Where pin number 5? Right here. if you're reading, looking into number 5 here. Okay. So positive clock to pin 14. That means the clock will be go into right here. For both up or down. However, you want up or you want down, depending on logic, apply to pin number 5. If pin number 5 at the logic 1, they going countdown. If pin number 5 at the logic 0, they count up. That's different with 193. Okay, if you get a question, just stop me, okay? This is just the timing. On this one, 160. That you get the left number 8, I think so. 160 BCD counter. That means counter count 0 to 9. Only up, not down. Okay, and in here we already explained to you. Clear active low, higher priority. If clear 0. And clock going 0 to 1. Then QA, QB, QC, QD equals 0. Now you see the difference. This IC completely controlled by the clock signal. Whatever you want to do, you must get the clock going 0 to 1. You apply the clear equal 0, output not 0. Until you apply the clock 0 to 1. And now they get clear. And sometimes you can see on this left more simple. However, more people get a problem, they cannot make it work. The thing is, you need to read. Okay? Again, this IC completely controlled by the clock. Whatever you want to do, they need the clock. So if you want to clear active low, you set clear equal 0. Output not 0 until you apply the clock 0 to 1. Same thing. Load active low. Second priority. You can set you want to load. However, if you apply ABCD, load equal 0, the output is not equal ABCD until you get the clock 0 to 1. Okay? And counting up 0 to 9 to 0. Okay, so any question on 24,160? This is a timing. This one we already done for the JK flip-flop. Only make sure you understand. JK, pin number 5, power, pin number 13, round. They get a 16 pin. but not 16 power or 8 will be round. No. If you connect wrong power and round for this IC, you cook it. Sometimes you're working on your lab, you touch on the top of the IC, you see the hot, some must be wrong. Now, try to see on this one. $373. That's a D flip-flop. But the last, I just try to help you to see how you make it work. If you say this IC, how many pins? $20, right? 1 up to 20. And like normal, 20th will be 5 volt. Pin number 10, just a half of 20 will be right. This just a like the flip-flop. Okay, how many input D? That will be 8 bit. The large. You understand that the last different from X trigger. So you see on the function table, OC, pin number 1, output control, active low. What that mean? When you say the pin number 1, you put an OC active low. Can you tell me what that, how much you understand on that pin? If that pin low, what happened?
You get output.
If pin number 1, output control low, what happened?
It's activated and you get output.
Okay, that only telling you. If pin number 1 low, whatever D 0 to D8 in here, inside, go out. And yet, what I mean is, whatever logic inside the IC will be go to the output. We're not talking about input, one D to D, okay? They just going out, they already inside the IC. Okay, so input CD, high, Q high. Okay, and the next one, okay, then let's see, 7D, Q. Let's see, C, let's see, what's C? What's C here? C here. C like the clock. but they're not a transition. Okay, that will be telling you what happened. C high, okay, and input the inside will be high, okay, that will be high, output high, okay, C low, okay, and if the D low and output will be low. Now I tell you what happened. If you get an input 1D, 2D, okay, I just pick only 2, okay, they're supposed to be 8. If you get a 1 logic here, you get 0 logic here, okay. Basically, they cannot go inside of the IC until pin 11 at logic 1, okay. Pin 11, that means pin C at the logic 1. Let's see here, pin 11. If you get a logic 1 here, so whatever at the input D will be go inside. They will stay inside here until output control 0. That will be go to the output. What happened if the pin 11 low? When you're looking into the scale function table, can you tell me how much you understand? If pin 11 at the logic 0, and what happened?
No change.
That means we're talking about right here.
The previous data.
No change.
That means data at the input D cannot be get into the IC. Okay? So the input D, they don't care. The thing is they cannot load in. And the output, no change. Whatever, it's still the same. Okay? So this IC very simple. You want the input applied to 1D, 2D, 3D, so on. If you want to go inside the IC, you have to apply 11, must be logic 1. If you apply logic 0, that cannot do anything. And when the input already inside here, you want to going out, OC must be 0. Last one, OC output control at the logic high. What happened? If you're reading that function, telling me, if OC at the logic 1, so what's going on?
The output have a high impedance.
Exactly. That will be telling you, pin 11, they don't care. Input D, they don't care. Output have to be high impedance. What that mean, high impedance?
It means there is no voltage.
You measure, you will be get any voltage. However, I can tell you, when they high impedance, that means at the output, right here, output here, they look like they get a very big resistance. Okay, very high resistance. The reason is they don't want any current flow into the IC. Okay, when they're not using it. Otherwise, they will be loading the current. So that's why you can see inside the system, they get too many types of the flip-flop or whatever flip-flop, but they must be get the output control. The thing is in the computer, data bus, you get 16 wire, for example. Address, you can get 32 wire. However, on the address, you get only one IC supposed to be used. And also the data on the data bus, only one IC can send the data out or receiving the data. But they get too many memory inside. So they have to get the circuitry to control, allow only one IC be on. Okay. So any question about 373? The large. You understand this one? Easy to understand like what? 374. Okay. This will be X trigger. That's only different. That means you want the input D go inside. You need the clock. Okay. The clock going 0 to 1. That is the difference between the last. The last you get a level. That means level 1. They allow input D go inside the IC. However, X trigger, they need the clock 0 to 1. So input D can be go inside the IC. Same thing, output control 0. Whatever data inside IC will be go into the output. The thing is that kind of the IC will be using a lot during the lab number 10, 11, or 12, or so on. 541. This IC will be 20 pieces. 20 VCC, 10 will be round. Very simple. That's what they're talking about buffer. Buffer means 0 in, 0 out. 1 in, 1 out. Nothing else. Why do we need a buffer?
To boost the signal.
I gave you an example. For pin number 9, input, I said 2.5 volt. What logic? At pin number 9, apply 2.5 volt. What logic?
On.
Logic 1. However, If you enable it, they're coming out here. They go to 4.5 volt. Now you understand why they need the buffer. The same logic one they coming in, but that's not a good logical one. Logical one, you want it at 5 volt. So that's why when they go through the buffer, they try to bring very close to 5 volt as much as we can.
Does that require more current?
Exactly. Increase the current. Logic, no change. One in, one out.
So that IC is technically hotter all the time.
Right.
Does it need a heat sink?
Now, the thing is just a logic, so that's not a critical frequency. They just try to bring to the standard logic. I give you another example.
Then
You
that,
get- Just a minute. 0.5 volt here. What logic? 0. However, when they go to pin 16, they get 0.1. You see that? Binary, they want logic 0 will be 0 volt. That means close to 0, much better. Our logic 1 is 5 volt. Close to 5 volt, that's much better. So that's why they need a buffer. And this buffer will be controlled by pin number 1 and pin number 19. Okay? 1 and 19 must be 0. So you get an input coming in, output coming out. Okay? Either one has a logical 1. Output will be high impedance. So that's why in here, they're talking about 3 steps. 3 steps mean what? 1, 0, G. Pin 119 is not 0. Output will be high impedance. It can be either 540 or 541, depending on the pin. Okay, this is the IC here. Okay, let's see.
Mr. Fan,
That will be 20. Okay, they given you the truth table. One apply for 540, one apply 541. This is using a lot everywhere.
does that specific IC have a heat tolerance where the voltage or the current will cause that IC to not operate correctly? Can that IC technically get too hot to where you won't get the accurate measurement?
Now, the thing I did is a logic, okay? Either to get 1 or 0. Digital will be not deal much with the tolerance. Not accurate. 2.5 volt, 1, 3 volt, 1, 3.5, 1. They not get a tolerance. Okay? So they don't need the accuracy. Analog, you measure the voltage output, plus or minus how many percent. Digital way already telling you. You want up to 5.5, logic 1. Or 0 to 0.8, logic 0.
Then those ICs have a transistor in it to boost gain then?
They get transistor inside. However, They get NPN, PNP inside the IC. However, NPN or PNP inside, they must working in saturation. Okay, we already talking about NPN, PNP. They can be what? They can be active for amplifier. They can be cut off or saturation. That for logic circuit. Same thing. Another one, 3-state buffer, 244. Only thing I can tell you, this different from the other two, 541, 540. This will be, they allow you to get 4 bits to going out. Okay? They don't have to be the same 8 bit. Coming in 4 bit, coming out 4. That means they get to separately for each one. Pin number 1, they allow 2, 4, 6, 8 pin in, and they going out 12, 14, 16, 18. And pin number 19, control for input. Okay, 11, 13, 15, 17, going out to pin 3, 5, 7, 9. So you see this is a different from the other buffer. The other one, 541, they control 8 bits at the same time. On this 244, they control 4 bits. Okay? You can get that 2-4 bit completely different. If you want both 8 bit in, 8 bit out, then pin 1 and pin 19 enable must be tied to ground. Okay, so what I want you to do is try to look over the coder 139. So you get 2 IC, 138 and 139. This for the IC 139. Okay, 138, they get the they get the 8, okay, combination, and 139, where they get 4. So reading that will be easy. Next time, when I'm talking about the lab, then we will go detail for you how they working. The thing is, next time we can get the memory. And after the memory, you get DAAC converter. Okay? Almost lecture will be done. However, the lab will be the problem. Again, if you get any question regarding into the lab, we already uploaded either Excel or your program. Or you build the circuitry, you run it, they not part. you can text to me. I can on Zoom with you to help you out. Don't take too much my time.
I also noticed that the student is starting to do some function declaration, function definition, and all that. Is that going to cover in your next lecture?
About which one?
Look like at the lab that's coming up, it require about function declaration, function definition, function. Are you going to go over the lecture with them so that way they understand how to use those function definition and declaration?
Declaration?
Yes.
Which one is clapping?
Well, DLab 7, 8, and 9 will require do function declaration, function definition, and be able to use that because you do the count. And so you want to give us a little bit of lecture on the function, how you declare to create a function and how to define it and all that. Because this is a tech one, they're brand new, they don't understand about using function.
I'm not quite follow what you're talking about function in
Okay, on the
software,
DLab, yeah,
or in hardware.
in DLab 7, it requires you have to do the function definition, function declaration, and then function definition. And then after that, be able to use it because you do the count down, count up. That is your function definition, right? So you're going to cover that, give them a little bit of lecture on how to do function definition and all that. How to declare function, how to define it, and how to use it.
Just a minute.
Okay.
193, right?
The lab 7.
Yeah, 193.
Yeah, that would be required to count, which is the counting up, count down.
Okay.
And so you have to define you define that so that way it's easier to.
Okay. Okay, that is 193. The left
Correct.
7.
Correct.
Okay, if you're looking on this circuitry here, we're already talking about 193 can be go up, go down. Okay. The way we design the circuitry, that means after they go up, then automatically they will be go down. And after they go down, they go automatically counting up. You already know. To count up pin 5, multiply the clock. Pin 4 must be logic 1. Okay? And otherwise, revert it. If you want down, pin 4 will be clock. Pin 5 have to be 1. Now, if you're looking on this circuitry here, I want to clear. Then PA05 have to be logical 1. Correct?
Correct.
For clear. Okay. And PA5 at a logic 1 and this also at a logical 1. 1 in the input NAND and output will be 0. 0 here will be preset U5. Output pin 5 will be 1. Okay? So you try to get the clear for U3. Also, they want you to make sure U5 pin 5 have to be logic 1. Okay, and this go to U1 pin 1. Go here. So if you get a logic on 1 in here, what happened? If you get a 1 input here, go to the NAND. So pin 6 supposed to be 0. All with and clock. And clock go to the NAND. They will be P clock. So they're telling you the clock go to pin number 5. Also, pin number 1 here at the logic on 1. You go to the NAND. They will be 0. 0 in pin number 10 here. Output will be 1. That's why when they count up, clock go to pin 5. However, pin number 4 have to be 1. And then now, in general, when they count up to 15 and the COBO, you see that? When they go low, that go to U4 pin 1, 2, right here. Okay? And basically that will be make the clock for U5 pin 3. D flip-flop. D flip-flop, if you connect not Q back to D, that means they will be toggle every time you get a clock coming in. Okay? So when they reach 15, you get a clock go into U5. They toggle. That means output pin number 5 was 1. Now they go to 0. 0 here, go back to pin 1 here. Then that will be change the counting up to the counting down. When you try to write your software, I already gave it to you here. You must be using the loop. Okay? If you cannot follow that flow diagram, and this is the one you will be need for your that program. Okay? We have to learn how to using the loop. So next time we're talking, if we get more time, we're talking about software. Then we'll be helping you how to writing the loop. Without the loop, you cannot do any lab. Like you're testing memory. Memory to get 1,000 location. You don't want to type in 1,000 test. You must be using the loop for I equal 1 to 1,000. Just few lines, they can do 1,000 tests. Okay? So that will be, for now, you want your software, you can copy exactly here. They will be helping you. And again, when you try to apply input, they say test load. You know what logic is supposed to be applied. Okay? Or test counting. Anything in here, we don't want you to writing anymore into the port A. Okay? I think we don't need that anymore. However, go to tab 21. You need to write to port A. Okay, 21. Right here. Okay? And the output here, only I get problem. When you getting the toggle, you find we want this one. Okay. That's clear. Okay, that's clear. Also, we need one. I correct that.
Yes.
Okay.
Okay.
That means we have to get the
Pick up the mass data.
math data
Yes.
for clear.
Yes.
Okay. Yeah, thank you, Sam.
You're welcome.
The thing is, I have to go to the lab more carefully, try to make it clear as much
Yes.
for the guy to do. Okay, now, after you get part on this, put A, B, C, D. Now only thing what you need, follow, apply input, that one you write, you put A, whatever data. You see that? And put C, you reading data. If you get the right thing in here, then your test program is supposed to be good. And I already sent you to Sam this program already, right?
Yes, sir.
Is it working?
Yes, sir.
Okay. The thing is, I try to find a way. I can try to transfer the lab into my iPad. Easy for me to help you guys to understand. And I think I know the way in order to do. Power, you know, using the different file I can upload into my iPad. However, Excel, they get a different sheet. Okay, schematic, key, port A, B, C. So I have to know how we can transfer everything. Otherwise, if I transfer now, they only transfer port A and C. They not transfer that program. They not transfer schematic.
You're wanting to transfer the Excel sheet or share the screen?
Transfer into my iPad, so easy for me to explain to you.
Right, so a lot of phones and devices have that device find. You should be able to just share the screen, kind of like a push function.
You mean if I want to share the screen in the iPad, okay?
You'd be able to, you should have a device find, and then that you should be able to show like a divided screen, like a share screen, very similar like Zoom. You
But
should,
the thing is, if I wanted to Excel, I have to get Excel in my iPad. I don't have it.
that's what I mean. Share screen, you shouldn't have to use
Yeah.
it.
That is, if you wanted to have to buy the software.
Well, that's what I'm saying. You don't have to. You shouldn't have to. You shouldn't have to have the software. You're just sharing the screen.
Yeah, but the thing is, I know how to do it. That means I can try to combine everything in one sheet. Then should be okay. Okay, so any question, anything?
Everything's good.
Okay, and I believe on summer, maybe we get more time for the lab. We see what's going on, what happened.
Okay.
Okay, so make sure if the one lab you already did it in the past, I'm not asking you try to repeat it again. Okay. However, if the thing in the past you're not done, you better do it. You know, it's not really hard for me to do on the D lab. Easy.
Right.
Easier than the level. Okay.
Okay, sounds good.
So, any question to me? If it's not, okay, good night. Have a good weekend, everyone.
Mr.
You too, thank you.
Have a good one.
Bye bye.